Ampere Circuital Law is an extension of Biot-Savart's law. We have read in Oersted experiment, or as per Oersted experiment, if a conductor carrying current is placed along z-axis, then magnetic lines of force are found to be concentric, in concentric circles at right angle concentric circles in a plane xy at right angle to length of the conductor. Hence, at any point, the magnetic field, at any point on an imaginary circle, the magnetic field is tangential to the element. Magnetic field is tangential to the element. Let us consider an elementary closed path. Suppose it is an element dl, and here magnetic field is tangential. Another point dl, here also magnetic field is tangential. So for any element, we can say that magnetic field is tangential. Consider a closed loop or a closed path. Closed loop for any element of length dl, B is tangential, that is B dot dl is equal to B dl cos 0, that is B dl. This B dl is known as line integral of magnetic field. This B dl is known as line integral of magnetic field. Summing of the total line integral across a closed path. Summing of total line integral of magnetic field across the closed loop, across the closed loop is integration of B dot dl, known as summing of total line integral across the closed loop is written like this: integration of B dot dl. This closed loop means it covers, and according to Ampere Circuital Law, according to Ampere's Circuital Law, this line integral of magnetic field across any closed loop or closed circle, across any closed path is mu 0 times the net current passing through it. That is, integration of B dot dl is equal to mu 0 into I, where mu 0 is the permeability in free space, where mu 0 the permeability in free space, and I the net current passing through the loop. Suppose this is a closed path. I1 is the current moving in upward, I2 is the current moving downward, again I3 is the current. Suppose these are the three conductors having current I1, I2, I3 are passing like this. Here, how to find out what is the net current? Now, by application of right hand thumb rule, if the thumb is along the direction of a conductor or length of a conductor or direction of current of a conductor, and curl of fingers is the direction of magnetic field, and then such current is taken as positive. If the thumb of right hand is kept along the direction of current and curl of fingers along the direction of lines of force, direction of magnetic lines of force, then such current is taken as positive. Thus in the figure, net current I is equal to I1 plus I3 minus I2. Because here magnetic lines of force is anti-clockwise in the upper face. That's why I1 is positive, I3 positive, and I2 is, that is, negative. Or Ampere's law, written like this: B dot dl is equal to mu 0 sigma I or j is equal to 1 to n. This law is found to be applicable for determination of magnetic field in case of complicated circuits like or diagrams like solenoid and toroid and long extended cylindrical surfaces. Suppose this is the amount of current, I is the current. Now imagine a circuit or a circle at a length r. As current here is upward, so lines of force will be anti-clockwise at any point for any element. According to Biot-Savart's law, magnetic field for an infinite conductor, according to Biot-Savart's law, magnetic field due to an infinite conductor at a normal distance r, the magnetic field B is equal to mu 0 I by 2 pi r, where r is the normal distance and I the amount of current, and r the normal distance from the conductor. So the Ampere's law, circuital law, can be proved with the application of this statement or the value found in Biot-Savart's law. If we start from B dot dl, we can write like this. Here B is equal to mu 0 I by 2 pi r according to our Biot-Savart's law, and dl cos 0, because for any element at any point, since magnetic lines of force are anti-clockwise, so angle between magnetic field and elementary length is always 0. Here the length is 0 to 2 pi r, so which is equal to mu 0 I by 2 pi r into integration of dl, that is 0 to 2 pi r. So this is mu 0 I by 2 pi r into 2 pi r, that is mu 0 I. Thus the law is proved using Biot-Savart's law. Hence we can say that Ampere Circuital Law is an extension of Biot-Savart's law. Thus Ampere Circuital Law is an extension of Biot-Savart's law. So in Ampere Circuital Law, it is observed that this statement is independent of shape and size of the closed path. Independent of shape and size of a closed circle. Closed loop or path. And this closed path, the closed path is known as, or the closed path or loop is known as Amperian loop. Amperian loop. And in case of state conductor, it is found that since B is equal to mu 0 I, or in the reverse way, we can find out that using this we can also find out magnetic field due to a state conductor. As was found in Gauss law, which was an extension of your Coulomb's law. So using Coulomb's law, we can justify Gauss law, and from Gauss law, we can also find out the Coulomb's law. Similarly here, you can say that Biot-Savart's law can be used to prove Ampere Circuital Law, and also using Ampere Circuital Law, we can find out the magnetic field due to a state conductor. Suppose this is a state conductor. Imagine a closed circle at distance r. Then at any point you can say that since current is upward, therefore lines of force is supposed to be like this. So for any element, if this is a dl, this is a magnetic component which is tangential to the length. For a straight conductor, with current I, the magnetic lines of force are in concentric circles. Let us consider a closed loop at a distance r. Now applying Ampere's circuital law, integration of B dot dl is equal to integration of B dl cos 0 is equal to B into dl limit 0 to 2 pi r, that is B into 2 pi r. But according to the law, B dot dl is mu 0 into I. Hence, B into 2 pi r is equal to mu 0 I, or B is equal to mu 0 I by 2 pi r. Thus, due to a straight conductor, a straight conductor, magnetic field is direct proportional to amount of current, and magnetic field is inversely proportional to the distance from the conductor. Thus field decreases. Thus magnetic field decreases. Thus B decreases with distance from the conductor. So magnetic field possesses a spherical or cylindrical symmetry. So magnetic field around a conductor, straight conductor, shows a cylindrical symmetry. Cylindrical symmetry.